So we continue our discussion with the topic on the topic process synchronization. And today we are going to look at a very interesting synchronization tool called semaphore. So in the discussion so far regarding the synchronization of processes and threads, we came across software-based solutions where we tried with different variables and flags, and we used them in such a way that the processes ensured mutual exclusion. That is, only one process will be executing in the critical section at a particular time. But we find that software-based solutions have their own problem. They were bulky. And we then went on to the hardware-based solutions, where we took help of instructions provided by the CPU, which could be utilized in an effective way to ensure mutual exclusion. One of these such instruction is a test and set instruction, where the idea was that you read from a memory location and you update that with a new value. So that was very effective in ensuring that you can create a lock. How? If you initialize that particular memory location with a 1-0 value, and then a process that reads that gets the value 0 and finds that because that memory location is 0, it enters the critical section while updating that memory location to 1, so that no other process can enter critical section. Because if any other process wants to enter critical section, will check that particular memory location and will find that the value has been turned to 1. And the process that is currently entered the critical section by making that lock equal to 1 has to finally make that lock equal to 0 and then come. This was the hardware-based mechanism that we found. But we also found that this hardware-based mechanism has to be atomic. That is, reading and writing, these two processes cannot be interrupted. And hardware instructions said that, okay, these are atomic. Well, but what about the processes that were waiting on that particular lock? So the hardware-based technique allowed only one process to enter critical section, and others were restricted and they were looping. So this kind of looping of that particular process we called as spin locks. And that is okay, as long as we were fine with disallowing that particular process. But the problem is that whenever that particular process or more than one process would be looping on that lock, there's no productive that is done. Every time the process would get scheduled, it will execute that while loop and will get stuck. And a lot of CPU cycles are wasted. So this was the major problem of spin locks. It's called busy waiting. Now there's one more disadvantage that busy waiting created. It was a priority inversion which happened. And it's a low priority task would actually prevent a high priority task from progress if the low priority task held that long. This was the problem that we found with spin locks. A possible solution to spin locks was that if a particular process starts looping on a lock, we could, instead of making that loop, we can put it to sleep. And that was the concept called mutex. So it's a specialized spin lock where for the process that gets stuck in that lock, that is, it does not get the lock until the currently running process who's in the critical section releases that. So for all of the processes that loop on that lock, whenever they see that the lock is held by someone else, they are put to sleep. This is the concept of mutex. So this in some ways saves the CPU cycles. But again, there is a problem with mutex that when the currently running process exits the critical section, it should wake up the sleeping process. It was fine. as long as you have one sleeping process. But if there are more number of processes that are sleeping on that lock, then the process that exits the critical section sends a wake up. But the question is, the wake up is meant for which of the process? Many processes can get woken up, and then there would be a huge context switch. This was one of the problems that was faced in using mutex. Then it was decided, well, we will maintain a queue, and for all processes which are waiting on a lock, we will put them in queue before they are put to sleep. And whenever there is a wake up from the process that exits the critical section, the process which is at the head of the queue will be the one that will wake up. This is the condition that was used. It was working fine. But we saw in the last problem, which is the producer-consumer problem, we saw that mutex is a possible solution, but there could be a situation where there can be a lost wake up. That is, the producer sends a wake up, but that wake up is ignored by the consumer. We saw the situation where, suppose the producer sends a wake up feeling that the consumer may be sleeping, but the consumer is currently not sleeping. So it ignores the wake up. This is called a lost wake up. So the wake up signal gets lost, and there can be a situation where the counter, which is a shared variable read by both producer and consumer, is the same value. Producer has also read counter equal to 0, and consumer has also read counter equal to 0. Because producer, if it reads counter equal to 0, produces an item, and counter, if reads counter equal to 0, it does not sleep. So, and there is, if this is how the context switching happens, there can be a situation where the producer, or sorry, the consumer reads this particular value equal to 0, and it's put to sleep. However, it should have woken up because the producer has already sent a wake up. But the wake up was sent before the consumer started sleeping. That is why the wake up could not be received. And now that the consumer sleeps, the control goes back to the producer, and producer now keeps on producing items. 1, 2, 3, 4 in this way, and finally fills up the entire buffer. When the buffer gets filled, the producer sleeps. So now we have a situation where the producer, after it completes filling up the buffer, goes to sleep. The consumer is already sleeping. Now this situation is what we call a tetra, where both the processes, producer and consumer, is put to sleep. This is one of the problems that may occur if you are using mutex. Okay. So then came, so there must be some other better way to handle this problem. And the problem that we are talking about, the solution to this problem that we are talking about, is called semaphores. So semaphore is the solution, or we can say the synchronization tool that can be generalized to handle complex problems. Semaphore is again a concept that was given by Dijkstra's, okay, in 1965, I think. He gave this particular concept that you can use this particular tool to perform synchronization. What is semaphore? Let's try to understand. Very, very simplistically put, it is nothing but an integer variable. That's it. It is an integer variable. So it's an integer variable that, apart from initialization, is accessed only through two atomic operations. This is the thing that we should keep in mind. It is an integer variable, and there are only two operations that can be done on this variable. Only two operations. And these two operations are atomic operations. That is, when you are performing that operation on the semaphore variable, the operation has to complete, only then you can stop the operation. It cannot be interrupted in between. The question is, what are these two operations? Well, the two operations that we are talking about are wait and signal, or down and up, or P and V. These are the same. Either you call it a wait operation or down operation or P operation, or you call a signal operation, up operation, or a V operation. Any of the three. This P comes from a Dutch word proberen, which means to test. So this operation, it's a wait or down or P, will be checking or testing the value of the semaphore variable. That is why it is called the name P. P stands for proberen, to test. Tests the semaphore variable. Okay. Down comes, if you will look at this expression, you will see that the down operation, which is working on this variable, it performs a check which says if the semaphore variable is 0 or a negative number, you loop, you do nothing, no operation. Okay? No operation. If it is a positive number, you decrement the value of S. Decrement the value of S. And that is the reason why we say that it is a down operation. You're decrementing. Or wait. Why wait? I'll show you when we'll see how semaphore can be used to perform this law. So this is the operation number one that can be done on a semaphore variable. Simple. A check. If it is 0 or less than that, you loop, no operation. If it is not, you decrement the value of S. This is the operation which we call wait, down, or P. So you will find in book, suppose we declare something called, let's say, semaphore. S is a semaphore, and we write P of S. P of S is actually this operation. Keep in mind this entire thing. Okay. Or if I say wait of S, wait, apply wait, this is also the same thing. Okay. Or I say down on S, that means the same thing. Keep this in mind. This is the first operation that will be done. The second operation, that is signal up or V, is this. As you see, there is no check, just there is an increment. And V stands for this Dutch word, which means increment. So this is like V of S, or you have up of S, or you have signal of S. So this is the operation that will be done. Just increment the value. Simple. Down means check. If it is positive, decrement that. If it is negative, you loop. So this is the one. Now let's see how you can make use of this semaphore. Is the semaphore variable clear to everyone? A simple integer variable that on which you can run only two operations, the down operation and up operation, wait operation or signal operation. How is it used to ensure synchronization? Let's see. Now, if S is initially set to 1, okay, let's take this. Let's see, so that we understand how it can be utilized. Let's say you have a semaphore S and you initialize this to 1. Okay. Now blocking semaphore similar to mean. If S is equal to 1 and you have a process say P1, let's say this is say, okay, say this is process P1 which is running, and somewhere down the line it applies the down operation on S. The down operation on S. So what? And this down operation is extended. It's the down operation is extended for the rest of the code. Let's say for this part, and here it is making an up. Now let me show you what happens. If this is the process called P1, and somewhere down the line, this is the code, somewhere here, it makes an up, a down on S. What is the current value of S? Let's look at what will happen. Because it applies down, this code will run. And it's an atomic code, so no interruption. What will happen? We'll pass the value of S, and there will be a check whether S is less than equal to 0. Is less than equal to 0? Is less than equal to 0? No. Okay, which means it will fall through this loop. It will fall through this loop, and S will now become, after this operation, S will become 0. Because S was initially 1, so S will become 0. So after this down operation, S will become 0. Now let's think about another process P2, which is also running. Okay. And it also wants to enter critical section. So it will also apply a down operation here. Now the moment P2 comes to this line and applies a down operation, that means this code will run. And this code will run means this line will be executed. This line is this check. For P2, it will find the value of S equal to 0 because S is currently 0 as made by P1. So what will happen to P2? P2 will loop. That's what we wanted. We wanted mutual exclusion. So now we have prevented P2 from entering critical section. Right? So as long as P2 will remain in this loop, P2 wants to progress, right? When will it happen? Well, when P1 is done. When P1 comes out of the critical section, it should turn on or signal the other process which is waiting on the lock. How? By either through a signal on S or up operation on S. Up operation of S means this code will run. And if this code runs, what will happen to S? The value of S will be 1. When the moment S is 1, and when P2 will get a chance to execute, P2 was stuck here, it was looping. The moment S becomes 1 as made by P1, when P2 now starts running, it will fall through this and will move into the critical section. Fantastic. So the semaphore can very well be used to perform the same thing as done by the spin locks. I can use this down operation and up operation to ensure that only one process is allowed into the critical section, which is nothing but the mutual exclusion. Okay, so this is the idea. Let's see that. So only 2 operations is what we needed. And these are the 2 operations that are supported by a semaphore S. Let's see. So the P operation that we are talking about, what is the idea behind that? That if you are applying the down operation on a semaphore variable, and if this S is less than 0, the process will get blocked and it will resume only after it is woken up. Who wakes up? Well, their waking up is to be done by the process that is currently in the critical section. We have seen that in the concept of mutex. So semaphore solves the first problem, the mutual exclusion problem. That is, if there are more than one process which wants to enter critical section, allow one of them, prevent others. And the second problem that was there in mutex, that is, what about those who are waiting on the lock? Should you put them to sleep? If you want them to sleep, well, that you will save cycles, CPU cycles, but then the producer or the process which is currently in the critical section, it should take the responsibility to wake them up when it exits the critical section. That was handled in mutex. If you are saying that semaphore is an alternative to all this, how does the semaphore handle the second problem, the waking up problem? So here it is that the down operation should handle both. It should not only handle the locking, it should also handle the waking up problem. So as you see here, it should also wake up. Because if a process is sleeping, there is someone who wakes it up. Where will this happen? The waking up process, in the up operation. In the up operation, it says, if there are blocked processes, then wake up one of them, as we said in case of mutex. And how it is? Well, it is just increment of your semaphore variable. This is it. So we found that S is a non-negative number and it is supported by the major operating systems, Unix, Windows. This is the idea behind semaphore. Okay, let's see the operation through which semaphores can be used to perform mutual exclusion. I've already discussed that. It is the same. So we initialize the semaphore with, this is the declaration of the variable, semaphore S. Semaphore is the data type, S is the semaphore variable. I will come to that when I talk about the POSIX semaphore APIs. We will see how semaphores are, how Unix or POSIX-based systems, they provide what functions to handle or work with semaphores. We'll see that. So for the time being, let me explain this through a pseudocode. So let us assume that S is a semaphore variable. Semaphore is the type. Automatically, it means that it's a semaphore variable. And let us initialize the S with value 1. So the structure of the process, any process PI in the ready queue will be like this. Wherever you will have a critical section, mind it, wherever you will have a critical section, you have to use a pair of operations above and below that, which will ensure that the critical section gets guarded. A PS-VS pair, see? And this will ensure that PI, whenever it gets the lock, enters the critical section and prevent others from entering. Beautiful concept. S is 1, so PS will, the moment if PI gets to, suppose S is 1 currently, and PI gets a chance to enter critical section, this will ensure the decrement operation, which means S will become 0 after this, and it will enter the critical section. It will fall through this while loop. So this S equal to 0 will ensure all Pj where j not equal to I are prevented from entering. And once it is done, it should make S back to 1 because VS is nothing but input. Simple. Okay. The solution is very, very general and can be used for any number of processes. So remember this, we will be very, very frequently using that. Critical section, whenever there's a critical section, you want to guard that, well, use a PS-VS pair and initialize S with 1. It will be treated as a lock. Okay. We'll see the usage of this. Okay. So this is what the general idea is. We used the lock variable, the semaphore variable. We use the down operation, up operation to protect the critical section. And obviously the lock has to be initially equal to 1. Does the algorithm satisfy mutual exclusion? Yes. Does it satisfy deadlock freedom? Yes. Deadlock freedom means it's not that there would not be any problem with the progress recall. It will not be that one will depend on the other. Does it satisfy starvation freedom? Can you guarantee that all processes that are waiting will once get a chance to enter critical section? Can you guarantee that? I mean, we don't know. It will be decided during the problem. So let's wait for that. Is it okay so far, the concept? Is it clear to everyone? Please feel free to interrupt me if you have not understood. Okay, we proceed then. Okay, so what is the advantage that we have? What did we get? Now we can modify the definition of wait and the signal operations to overcome the need of busy waiting, the problem that we had in case of spin locks. So when a process executes wait and finds that the semaphore is not positive, it gets blocked. Okay. Now this block operation that we have seen, which semaphore, which happens due to semaphore. Now here we can make a change. The change is that all the operations, okay, as you see here, the block operation will place the process into a waiting queue. That's the thing that we should be looking at. And this waiting queue is also associated with a semaphore. This is important. So the semaphore, which is deciding that only one process will enter and others will wait, they are not spin locking. They are waiting in a queue. And that queue is associated with the semaphore. Why? Why is it associated with the semaphore? Because all processes are waiting because they have not got the semaphore. Because when they are working on the semaphore, they see that the semaphore has currently not become positive, and that is why they are waiting. So we see that the queue in which we keep all these processes are associated with the semaphore. Okay, this is the thing. So let's try to summarize. Semaphore is a variable. It will have only two operations, and there will be a queue associated with every semaphore. That queue will maintain the list of processes that are waiting on that particular semaphore. Okay. So the process state of the process which goes into that particular queue, the system will change that the state of that into waiting, okay, because it's waiting in the queue. And then the CPU scheduler selects another process to execute. That's it. So it is because it is waiting, so we put it into the queue, very similar to how we handle the ready queue during scheduling. Okay, so it's put into the queue. Okay, now suppose the currently running process has come out of the critical section and it sends a signal. Okay, so that means one of the process will be restarted, which the ones which were waiting on that particular signal. Okay. And obviously, because the process is now ready to be executed, its state is changed from waiting to ready, and the process is now put back into the ready queue. So it had been moved from ready queue to wait queue when it was waiting on the semaphore. And the moment it gets the semaphore, one of the process that were waiting gets the semaphore, its state is changed from wait to ready. This is something that should be kept in mind. Okay. So the first problem is solved. locking problem, mutual exclusion. Second problem, process synchronization. What do we mean by that? We mean we want to have an ordering of the running of the process. Suppose there are two processes P1 and P2, and I want P1 and P2 to run, and they are being scheduled. Sometimes P1 is running, then P2 is running. The scheduler is taking turns. Now, at some point of time, I want no, P1 should be stopped here, and P2 would be allowed to continue. But this will not happen because scheduler will in any case take P1 and progress. But I want to do this. Even if scheduler allows P1 to progress, but I do something by which P1 will get stalled, P2 will proceed. And after this point, I will again allow P1 to move through. I want this to happen. How can I do it? I cannot in normal way because P1 and P2 are scheduled by the scheduler. How can I do it? Here is the way to do it. So this is what I will be using semaphore for. So I will be using a value of S. Okay. And then what I'll do is, if I initialize S equal to 0 and I put a PS here, because S is 0, the moment I put a PS, P1 gets stalled. P1 gets stalled. Because we just saw what PS does. PS checks whether S is equal to less than equal to 0 or not. Yes, S is 0. So you will loop. So you just put a PS and P1 gets stuck. P1 does not progress. Okay. But P2 has no such PS here. Now, after P2 reaches this point, say point number B in the code, P2 gives a VS. P2 gives a VS. The moment P2 gives a VS, that's an indication or a signal to the process which is waiting. So what will happen to S? S will increment itself. S will become 1. If S is 1, when P1 now gets scheduled, it will progress. See how by using a PS-VS pair among two processes, I'm able to stop one and allow the second one to progress. And then it is responsibility of the person who's progressing to wake up the other one. So P2 is actually waking up P1. This is what I mean by process synchronization. Both of them, they have a ordering. How do you ensure this? So you can say that semaphore is not merely a variable. It is actually a record. Why it is a record? We just saw that semaphore is not only a variable, also there is a list or a queue that is associated with that particular semaphore. And the contents of the queue are the processes that are waiting on that particular semaphore. So it's not just a variable, you can say. Literally, it's a variable, but when you talk about semaphores being used for synchronization, you should think that it's kind of a record where there is an integer that is used for locking and unlocking, and it also maintains a list of queues that are waiting, a queue of processes that are waiting on that particular semaphore. That is why I have written it here as like, it's a semaphore which is of type record. I have used a pseudocode notation, not any specific notation of a language, but you can write any, whatever syntax that is followed for a particular specific language. So let's say semaphore is a record. In C, you call it a structure. And then there are two elements in that. One is the integer and the other one is a process, the list of processes. So a semaphore has an integer value and a list of processes. So when a process is waiting on a semaphore, it is added to the list of processes. That is very important. This will ensure that you also maintain a queue of the processes. It's not only just a locking mechanism. And the signal operation, the P operation, this is done by the P operation. And the V operation, it removes one process from the list of waiting process and awakens it. Very similar to what you saw here. Here, this is a list of only one process, right? The list that is maintained by in S is two processes. I mean, only two processes that can be sleeping. And currently it's P1 that is sleeping on S. So the moment P1 is sleeping on S, if you apply VS, so this VS will ensure P1 to be read, removed from the list, and awaken P1. This is how you ensure. Is it clear to everyone so far? Is it clear, the concept of semaphore, how it works? Any questions? I'm going very slow so that you learn the concept and realize, introspect. Is it clear? The basic idea of semaphore, how it can be used for lock and how it can be used for synchronization. Okay. Next. Let's see how semaphore can be used for synchronization. We have already seen the locking mechanism. We are just adding an additional term in that. Okay. So because we now said that PS is not merely an integer, it is kind of a record with two elements, an integer as well as a list. So the first value that PS, the first operation that happens in PS is decrement of the value of S, the integer value of S. And then there is a check whether that value has become less than equal to 0 or not. If it is less than 0, it has become a negative number. Then you have to add this process to the list. Why? Because now it's a blocking process, right? If it is a blocking process, that means you have to put it into the list. And just the opposite. So whatever I just explained in terms of text has been written as in the form. So BS is first increments the value, then checks whether it is less than equal to 0. If it is, it removes it from the list and picks it. Okay. Now in the classical definition of semaphore, the semaphore value is never negative. We just saw that, isn't it? The one that was actually given by Dijkstra, it just considered S to be an integer and it said that S can never be a negative value. But this implementation that we have modified, this is not defined by Dijkstra. Dijkstra defined it as an integer variable, that's all. But we introduced a Q on along with that. So this modified definition of S and V, the P and V of S that we are talking about, it says that they can have a negative semaphore value. So semaphore can have a negative value. Okay. What does this negative value actually mean in this modified definition? It will mean that there are processes which are waiting, and the magnitude will mean that the number of processes that are waiting on that particular semaphore. See, all processes that will be blocked will eventually be a negative number, isn't it? Suppose all processes whose, because there is only one process called PI which started off with S equal to 1, with S equal to 1, it started off with S equal to 1, sorry. It started off with S equal to 1. Let's see the idea. There is a PI process. Initially S was 1 and the process PI is the one that got the first chance to check S. It found that S is 1. It entered the critical section and before entering the critical section applied a PS operation, and that is the reason why S becomes 0. So when PI applied the PS operation, S became 0. Now think about all other processes Pj that are going to check this S. All other processes. If you follow this PS operation, the first thing that will happen is for any Pj, the value of S will become -1 because the current value of S has become 0 and this will be 0 minus 1. Not only -1, it can be -1, -2 because all other processes, if Pj makes it -1, there is a process called Pk. If that will check S, it will reduce it further to -2 in this way. Look, and then because it is a negative value, it will get blocked and will be added to the process queue, which is waiting on the semaphore. So that's the -2. So if you look at that particular queue, okay, if you look at the current value of S, so if you look at, let's say, the current value of S as seen by Pk, you will see -2. So this S value will tell you that there are two processes that are waiting on that particular semaphore. That is why it is said that the magnitude of the S will give you the number of processes that are waiting on the semaphore. It has nothing to do with the classical definition of semaphore, which says that it will always has to be positive. It is just the modification that we have made in the definition of semaphore that will tell us that how many processes are actually waiting on that. Okay. Is it clear to everyone? Please let me know if you have any problem. Is it clear, this particular negative value? We have modified the classical definition to introduce this idea. Clear the concept? Okay, let's move further. Here you go. I have already discussed this. It is the illustrative example. Here you see there was a semaphore called S, which is initialized to 0, and you want to stop this process J from progress. So process J moves till this point, and here, because you have applied a PS operation, S becomes equal to 0, which means PS will block that. It will block Pj, and now Pi will progress. So Pj gets blocked at this point. Now it is responsibility of the process Pi to wake up the sleeping process Pj. So when it gets it here, it sends this Vs, which means S plus plus, which is nothing but S equal to, so this actually implies S is equal to 1, and that eventually allows Pj to. See how beautifully the concept has been, interweaved between the two processes. Okay. So what is the ready queue in this? What is the wait queue? The semaphore, the queue on the semaphore. It's like, let's say, two processes with only currently the moment it is PS, Pj goes into this wait in this queue, which is waiting on the semaphore S, and Vs will pull this out. Whenever there will be a Vs, it will read this Pj and will remove it from the queue. So there is no process now in the wait queue.
Hello, sir.
Yes.
Sir, the value of S will be -1 and 0 for PG and PI, because if we are using the modified version of semaphore, we are starting with S equal to 0, then PS would make it -1 first and then check.
No, in this case, it is just an idea. Please don't
Okay, sir.
apply that here. It is just to show you that how semaphores can be used for synchronization. You have to modify it accordingly if you want to go with the modified one. It is just to show
Okay,
you
sir.
that it can be used for synchronization.
Okay, sir.
It's again the same thing. We have just explained it with up and down, and yeah. Now, semaphore can be used not only for two processes, but for many processes, for synchronizing many processes, as you can see here. So there are three processes, P1, P2, and P3, and you would like them to be synchronized. Question is, how many semaphores would you use? How many semaphores would you have to use? That's the first question. Second question is, how are you going to use the semaphores so that they can be synchronized? Let's see. So we have used two semaphores, semaphore S1 that is initialized to 1 and semaphore S2 that is initialized to 0. Both are semaphore type variables. So S1 is 1, S2 is 0. So what will S1 do is, let's see, you are process P1, it is 1 by the way. So you have applied a down operation or a P operation on S1. So what will be the value of S1 after this? S1 after this will be 0 according to the down operation relation. So P1 will enter critical section and will execute A. Okay, will execute A. Then we'll up S2. Not S1 but S2. So let's now come to P2. And P2, if you have started off P2, P2 is having down S2 and up S2. So S2 is 0. Down S2 means P2 gets blocked. Okay, P2 gets blocked. So there is no chance. Let's go to P3. P3 also starts with a down operation. So S2 is -1. So it becomes P3 is also blocked. Okay, good enough. But P2 is blocked on which semaphore? On S2. P3 is blocked on which semaphore? S2. So here you have a situation. Nobody is waiting on P1. Nobody is waiting on S1, by the way. So S1 semaphore is not used except for P1. Nobody is waiting on that. Okay. So the situation is that if P1 wants to enter again, it will get blocked itself. So if P1 wants to enter again, let's try to understand. If P1 wants to enter again, it will get blocked. Why? Because P1 now will see S1 equal to 0 because S1 has not been turned to 1. Why? Because there is no up operation on S1. Who will turn S1? It is P3, but P3 is not working now because P3 is currently blocked. When P3 will exit critical section, only then it can turn on S1. This is the situation. So A or P1 executes, then all three get blocked. Okay. But interestingly, if P1 was currently running in the critical section, right? So here is an up operation that it has given. So P1 is ensuring that P2 progresses or P3 progresses out of the two, whichever. So whoever gets the value of S2, it progresses. So if P2 progresses, if it is P2, fine, P2 progresses and makes an up so that P3 can also progress. But if this up is meant for P3, so P3 will progress and will make up S1. Will make up S1. Please understand this. Let's say it is the other way around. Let's assume that P1 after exiting critical section has sent an up, but that up is meant for P3. Okay, so P3 will execute this. So there will be an execution of A, there will be execution of C, and then there is up S1, by the way. So up S1 means you go back to this. So P1 is free to execute, not P2. P2 will get stuck. So B will not be printed. Again, there will be an A. Again, if there is up S2, okay, so suppose by the time again P3 is there. So what you can see is there can be many possibilities. That is why we are writing it as, in this case, the star. Star means that you can keep on repeating. Take for example, if it was initially P1 and then followed by P2. So what happens? Down S1, up S2, this progresses up S2. Up S2 means again P2 is free to execute. Also P3 is also free to execute if P3 is blocked. So I can have in this way, like A, B, then again I can go to B, or I can have C, or I can have A, B, B. See, look at the way in which I can have this condition, this print, I can have this print, I can have as many B's as possible. If you go on moving in this P2, you will never come to P1. Think about the situation. You once started P1, printed this A, then you made an up operation and you went into P2, and P2 is just a pair of up and down for S2. So it can go on looping in this way. This way, it starts on this, and this up is meant for itself, let's say. That means again P2 can enter. Okay, again P2 can enter. Again it can. So it can go on in this way. So every time there's a loop of P2, a B is printed. So it can be one A, then one B. It can be A, then two B's. It can be A, then three B's. It can be A, then multiple B's. That is why we have written it as A, B star. And somewhere down the line, this up is also meant for C, if P3 is also waiting. So then you can also print C. And this entire thing can have different variations. That is why this is the all possible prints that you can see. See how we can generalize the two. You are taking a course on theory of computation. Can you identify this notation? Can you identify this notation? We normally represent this. Can anyone tell me something of this? Yes? We normally use this notation, right? Anyone? Yes, Pankaj, you are absolutely correct. Regular expression. Okay. Okay, let's proceed. Now, will this guarantee correct synchronization? No. No guarantee. How? Let's look at the situation. Suppose this is P0 and P1, and we have two down operations. There's a move one. And the situation that you are explained through this is where you are transferring money between two accounts, S and Q. You want them to happen. Let's say you first withdraw, and then you read the account. These are two transactions that are happening. You withdraw some money and then you read the account. Now suppose you read the account first and then withdraw, you will get a false result. So synchronization is very important. The ordering is important, or else you will have different result than whatever you see. So it's very important to know the ordering. Okay, and say you are moving from one account to the other. From A to B, you are transferring money. So money is transferred from A to B. So after the transaction, the amount of money, let's say X amount of money has been transferred from A to B. So the initial value should be subtracted from A, and a new value should be added to A. Correct? A should get reduced by X amount and B should get added by X amount. Now, if these two things do not happen at the same time for the reading and writing, you will have false results being shown. Okay. So how are you ensuring that? Are you ensuring it through semaphore? Let's see. So we are using two variables, two semaphores, S and Q, to ensure the two accounts. We are first doing a down operation on S, and S and Q both are initialized to 1. Then we are doing a down operation on Q, Then we are performing a move operation, that is the database is being touched. And then we are performing an up operation S and up and Q. And we are following the same thing just in reverse order for P1. Does it work? Does this work? Can anyone, I have given the solution here, the solution is written. Can you explain why is it going into a deadlock? Anyone? Just realize for yourself and try to answer to this question. Why is it a deadlock? What is a deadlock? A situation where one process waits for another process and that process in turn waits for the first process. And both of them get stuck and they do not move. So how is it happening?
We can have a situation where P1 has acquired the has called the down on queue, and then there is a context switch, and then P0 starts executing, and then it stuck in the second statement.
Absolutely. Just think about a situation where this fellow did this down operation, then there's a context switch and he did this, and both of them now have get stuck. The value of S has also become 0. The value of Q has also become 0. Now, if it comes back to P0, this will get blocked here. And if it goes back to P1, this will get blocked here. And nobody moves. That's the problem. So it will go into a deadlock. You cannot guarantee. Remember this, and this is a very, very common problem that happens. If you do not choose your order of semaphores correctly, you will end up into this deadlock situation. It's a very, very common problem. It's a very important problem. You should understand the ordering of the semaphore that you are going to use in your solution. If you have a different order, it may lead you to deadlock. Okay, so keep this in mind. Negative value semaphores, we have already discussed about that. I'll just reiterate that it's nothing but the number of processes that are sleeping on a particular semaphore. Okay, now comes the type of semaphore. Semaphores are of two types: counting semaphore, where you have an integer value, and binary semaphore. Binary, as the name implies, just takes two values, 0 and 1. And interestingly, you can implement a counting semaphore as a binary semaphore very well, because counting semaphore can also reduce the number of counts to only 0 and 1. It becomes a binary semaphore. We will see this later. So for the time being, let me quickly move to so negative semaphore implementation. I am not going into this because you already have seen the use of mutex. We have already discussed about this, that semaphore can be treated actually as a record. And if the value is 0, you put it to sleep and add it to the process. I've already seen that. Yeah. Now we are in a position to discuss about the three classical problems, and they are very, very interesting. So the three classical problems that we are going to talk about are, first, the producer-consumer problem, which we have already seen. We had seen two variants of producer-consumer. One was the normal solution of using two pointers. The other one was using mutex. Mutex did not work out because there was a problem of lost wake up. Can I solve that using semaphore? The first question: how many semaphores should I take? How many semaphores should I take? I've written the code. It's for you to see, but I want the answer why. how many semaphores should I take? What is the utility of these semaphores, each one of them? Tell me. Anyone? How many semaphores should I take? Yes. I have used 3 of them. Why do you think there is 3? What are these 3 used for? No idea? Okay, let me give it one by one. Go back to the producer-consumer problem. What is the problem? There is a buffer, there is a count. The items will be created and put in the buffer. The count will track of what is the current number of empty or full slots. Agreed? So these are the 2 shared variables. This is a data structure, which is the buffer and the count. So in my code, wherever this n and count will come, they will be the critical section. So if they are the critical section, I have to guard them. And for that, I need a lock. So I will use a binary semaphore, which is, I have given a name mutex, and it is of type semaphore. You can give any name. It's not necessary that you give. Please don't confuse it with the mutex that we have used. Okay, it is just to give a name. You can give any name. This is the one that is used as a lock, this semaphore. So this will be used as a pair. Have a look at that. Wait and signal. Wait and signal. Just see this pair, wait and signal. And mutex is initialized to 1. So if you use a wait or a p operation, you call it wait or p. You may call it p on mutex, both the same thing. So if you use a p or a wait, what will happen to mutex? It will become 0. And the current process will be allowed inside and it will be made 0 so that other process will be prevented. So if you use a PV pair, you are actually protecting this, whatever is inside this 2. So whatever comes in between the pair of PV, you are protecting that. Why have we protected this? Because we are using the buffer, you are using the insert operation, and insert operation will be applied on the buffer, which is a shared data structure. That is the critical section. So this is the critical section, because it's the buffer, which is the shared data structure. So that has to be guarded. So we guard this by the PV pair. We guard this by the PV pair. So the first semaphore for lock unlock of the critical section, and that particular semaphore will be a binary semaphore that will have a value of 1 initialized. What about the others? What is the other 2 semaphore for? Keep track of how many processes are sleeping on either of the producer and the consumer. So I am using an empty semaphore. Name is empty, which is initialized to n. So it's a counting semaphore. It can have any values. And I have another semaphore by the name full, which is initialized to 0. It's also a counting semaphore. This too will keep track of how many processes are sleeping. Okay, let's come here. If you are a producer, you will first produce the item, and then you will apply a down operation on empty. What will this do? Why did you apply a down operation on empty? Down operation on empty means, because I'm a producer, right? And if I do a down operation on empty, what have I done? I have reduced my n to n minus 1. It's a counting semaphore, so I have reduced my n to n minus 1. Okay. Now think, the first producer produces the first item. Should it get blocked here? No, because it started with empty n. It just made n-1 and then it fell through into the second line. This line is a wait on the mutex. On the mutex, it will become, mutex is 1, so it will become 0 and will lock so that the consumer should not disturb. It will fall into this line, will insert the item, and then it will signal or V. So the buffer is free now. And then it will go into the up operation, which is up of full, not empty, up of full. Why? Okay, remember, this is the check. This is the check if the buffer is full. Go back to the mutex solution. Remember what we were doing? We are using an if condition. If count equal to n, then go to sleep. We are doing that same thing, except that we are just using a down. What is the down operation? While the semaphore variable less than equal to 0, do no operation. So as long as it is a positive number, which is n, or anything less than greater than 0, it will move through this. So this is the check that we are doing. And what did the producer do once it came out of the critical section? It should wake up the sleeping the consumer. This is what it's doing. This is waking up the sleeping consumer. That's what it is, right? And this is what is done by the consumer. Exactly the same thing. This is the check whether the buffer is empty. Just compare this with the mutex solution and you will get the answer. And this is the check whether it wakes up the producer. The good thing about this is that there will be no lost wake up. Why? Because you are keeping track of how many processes are sleeping. So there is no chance that even if there is a context switch, your wake up is lost. You cannot have that. So even if there's a up which is being sent, and previously remember that wait which was or wake up which was sent was lost, in this case it's not possible. This is the solution of the producer consumer problem using semaphore. Clear? Okay. Let's move to the reader-writer problem. Okay. So what is this reader-writer problem? The reader-writer problem is, let me give you the basic introduction and then we'll see the solution. Okay. So the problem is, so the next problem that we are going to talk about is the reader-writer problem. This is again the classical synchronization problem that we are planning to solve, and we'll see the solution through the use of semaphores. So what is the problem, first of all? The motivation is that often we need to access a database and multiple processes would like to access the same database. So the database in this case is our shared data structure, and the code where the particular database is accessed, that's the critical section. The rule is there are two groups of processes, a reader process and a writer process. So multiple readers will be accessing the database simultaneously. And a writer process, it needs to have exclusive database access. Okay, so this is the thing that we should keep in mind. There are two kinds of users, the reader process and writer process. The writer process will be exclusively having access to the database, and multiple readers can access the database. That's it. Please try to understand. Only one writer at a time, multiple readers can be allowed simultaneously. So tell me, how many semaphores do I need? How many semaphores do I need? Yes. How many semaphores? And why are they used for? So as you see here, we have used two semaphores. One is called the mutex and the other one is db. And both of them is initialized to 1. So the first one, and in addition to that, there is a count which is initialized to 0. What is this count? This will keep track of how many reader processes we are having. So this is, as you see here, number of reader processes. We said that the reader processes can be multiple reader processes. Multiple reader process, only one writer process is allowed. Let's try to understand the situation. Suppose if there is only one writer, or a writer is currently touching the database. Listen to this. If there is a writer that is currently accessing the database, you should not allow any other writer or any other reader to access the database. Agreed to this? All of you agree to this? I said, if there is a writer that is accessing the database, no other writer or no other reader should be allowed to access the database. How are you going to ensure that? We have decided that we are going to use a semaphore DB that will control the access of the database. So look at this writer process. This is the writer process. So the writer process is checking, first of all, the DB semaphore, and it is applying a down. What does it mean? It means if there are no other writers, the first writer that executes this process or this executes this code will make DB, will check the value of DB. It will find DB equal to 1. This will check DB. It will find DB equal to 1. It will itself enter the critical section and will make the current value of DB equal to 0. So itself will touch the database. It will write to the database, and this DB equal to 0 will prevent any other process from any other writer process from entering the database or from accessing the database. Agreed? So this particular line ensures that no other writer process can enter if this writer is currently accessing the database. Let us see if the readers are also prevented. Let's come to the reader code. So this is the reader code. Let's see what is there in the reader code. In the reader code, there is a down operation, but before the down is done, so let's say the reader is scheduled. What will happen? The reader first sees a down operation on mutex. What is mutex? Well, mutex is controlling the access to RC. What is RC? The count which keeps track of how many readers are there. How many readers are there? But you may ask, sir, you said that multiple readers can be there. Yes, multiple readers can be there. But the updation of the reader count, that is a shared variable. Reader count is a shared variable. When you are updating that variable, that should be protected. That is why we are guarding that because this is the critical section where we are updating the value of the read count. This is the critical section. We are checking the value of read count. Because we are using the read count variable, which is a shared variable, that has to be protected by a mutex. Mutex means a log, so up-down pair. So as long as you are handling RC, you have to guard that within up and P and V, which we do. What are we doing inside that? First, because you are starting a reader process, so the first thing you do is you increment the number of readers. So number of reader will increase. If there was no reader, so the value of RC was 0. Now after this, RC will become 1, which means that at least one reader is currently reading. Okay. What will you see? If RC is equal to 1, which means if there is one reader, what should you do? You should make down dB. Down dB means the value of dB will be made equal to 0 because dB is 1. If the reader started first. And what will happen to this line if the writer started first? If the writer started, then dB is already 0. And executing this line will block the reader. Look how beautifully we have done. If the writer started first, it had made dB equal to 0 by this line. And let's say the scheduler now picks up the reader. The reader first makes itself 1 to show that one reader is currently working, and itself gets blocked in this line. So the reader gets blocked. Okay. Fine. So this writer code has ensured that if you are the writer, you are preventing any other writer to enter through this line. And you are also preventing the reader, because the reader process will also be using down dB. So you are also preventing the reader process to enter if the writer is already accessing the database. Okay. Now let's go the other way around. Suppose the reader was the first that started. If the reader was the first that started, then the first reader will first make RC equal to 1. We'll check if RC is equal to 1. It will find yes, RC is 1. And we'll make the down dB. That means it will make dB equal to 0 here. And itself will enter or go to the next line, where you will find up mutex. So mutex again becomes 1. And you fall into this line, where you are reading the database. Okay. Now what does this do to the writer? It prevents the writer. Because now, if the writer starts checking, if the writer, suppose after this line, the writer suddenly starts, writer will execute this line and itself will get blocked. So if there is a reader that is currently reading the database, you have prevented any writers from entering the critical section. This you have ensured mutual exclusion between reader and writer. Are you allowing other readers to progress during the time? Yes. Let's say reader number 1 has made this situation. The reader number 2 also enters and executes this code. No problem. What will reader number 2 do? Will reader number 2 get a chance to execute this line? Yes, because reader number 1 has upped the mutex. So no problem. Reader number 2 will execute this line. Will first fall down the mutex, that means the mutex will become 0. It will go into this line and will make RC equal to 2. Quite naturally, because the second reader has just entered. So the number of readers now are 2. Will it execute this if block? No, because you will find this if is not equal to 1, because if RC is 2 now. So it will not execute this line. So there is no point in again making the down. Down will remain at 0. dB will remain at 0. What will it do next? It will up the mutex. So the mutex will again become 1. Why? You may allow the third reader. The third reader can again enter, It will down the mutex, so mutex will become 0. We'll make RC equal to 3. Will it execute this if block? No. Again up the mutex, and in this way, many readers can be allowed to read the database because all of them will pass through this line and will reach here. There is no problem in reading. You can allow as many readers to read. So you are just preventing writers from entering and multiple readers are there. Now the question is, when the readers will come out, in what order will they come out? It will be this way. Keep this in mind. Again, the same process, except that this entire thing that happened with RC equal to 1 now happens with RC minus 1. So after all the readers are there, let's say there are 3 readers currently. What will you do? You will first down the mutex. Why? Because you are going to touch this RC. So the first thing is you should lock the mutex. Mutex is currently 1 because when the last reader had done this up, it had made the value of mutex equal to 1. So the first thing you do is you make the mutex equal to 0 because you're going to touch this. You decrement the value of RC. So RC now becomes RC minus 1. RC's last value is 3. So RC now becomes 2. Is RC equal to 0? No, RC is not equal to 0. So there is not yet time to signal the writer. So keep quiet. Do not signal the writer. What to do next? Make them up the mutex. So mutex again becomes 1. So mutex here becomes 1. Next, the next reader again downs it, makes it 0. RC minus 1, RC becomes 1. Is RC equal to 0? No. So it is not yet time to signal the writer. Keep quiet. Up the mutex, mutex again becomes 1. The third reader is going to leave now. Down the mutex, mutex again becomes 0. RC minus 1, RC becomes 0. Oh, is RC 0? Yes, it is 0. Now what should I do? You should signal the writer because you are up the DB. DB is the one on which the writer is waiting. So here you are signaling the writer. The writer will start and yourself make the mutex equal to 1. So the 3 readers have come out. Now you have signaled the writer that you can use. Beautiful solution. Understood all of you? How we are solving the reader-writer problem? Is it clear? Okay. The question is, who is more likely to run, the reader or the writer? Who is
Reader is more likely to run.
Reader is more likely to run. Why?
So because of the DB, we have semaphore DB. After the first reader comes, we will down it, and then the writer will not be allowed.
Let's see. So no reader is kept waiting unless a writer is currently in the critical section. That's what we have decided. If there is a writer in the critical section, no reader is kept waiting. So the writer process may starve if readers keep coming in. Hasn't seen that. If the number of readers keep on increasing, the writer will never get a chance. That is the problem. Okay, because the writer is held by semaphore DB, and if the readers come in, they will never get a chance. This is the problem that we face with this solution. So what is the solution to this? How can you be more fair? To be fair, we have the reader-writer problem. It requires no writer is kept waiting once it is ready. Okay, let me give you the solution. Here we have the solution, where we are actually giving more priority to the writer. Okay, we are giving more priority to the writer. So the writer, if it is there, will be running. So I'm not going to discuss this because we don't have time to do that. And I'll just introduce you. It's already there in the slide. Please go through that and look at the solution and convince yourself that how this particular, in this solution, the writer is given more preference. There are two solutions. The writer's priority is increased in attempt 2 and in attempt 3. We are trying to do that. Go through this. Okay. I'll end up today's lecture with the final synchronization problem, and it is called the dining philosopher's problem. So please pay attention and listen to this. It's a very, very interesting problem. The problem is this. You have 5 philosophers, as you can see on the right hand side, the diagram, which are marked in circle. And there are 5 chopsticks. So there are 5 philosophers who have a plate kept in front of them. Okay. Let's name them. Say, okay, here they are given 6 of them. So let's name them A, B, C, D, whatever. And there are plates where you have noodles served on them. Okay. And then there are chopsticks through using which these philosophers will be eating them. The condition is that the philosophers do this. They think, they take a fork one at a time. So this is, let's say I'm talking about philosopher A. So for philosopher A, this is the left fork, this is the right fork. For philosopher B, this is the left fork, this is the right fork. For philosopher C, this is the left fork, this is the right fork. Look how left fork for one becomes the right fork for the other. Okay, get this thing. So the rule is that one philosopher will pick up one fork at a time, then it will eat, and then it will put back the fork. This is the condition. You will take the fork, left fork first, then the right fork, eat, then we'll put back the left fork, the right fork. This is what we decide. To eat, you need 2 forks. And the condition is that you have to pick up 1 fork at a time. What is the problem that can happen? We'll see that there's a problem of deadlock, there's a problem of starvation, and there's a problem of conflicts. I'll introduce you to the problem, and then we'll see a quick solution to this. This problem is actually the problem of resource contention, where you have many resources, many processes, limited resources, and all of the process, they want that resource. Okay, so each process in this case needs 2 resources. Think that the philosopher is a process and it needs 2 sticks. So these 2 sticks, 2 forks are the 2 resources. And the problem is that if you assign both the fork to a particular person, then somebody else will not have the fork. That is the whole problem. See, if there are 5 people and there are 5 forks, and you assign 2 forks to, let's say, A and 2 forks to B, then what about C, D, and E? They don't have anything to eat. And if this is what happens, you actually cause C, D, E to starve. You should not do that. You should have a fair solution. This is the problem. Let's look at the situation. This is the problem that we have. And everybody is trying to pick up 1 fork. But you require 2 forks to be picked up. So nobody is able to eat. Look at the situation. This is a deadlock situation. The previous situation which I was discussing is a starvation situation. And this is a deadlock situation where everybody is having a left fork, but nobody is having a right fork. So there is a problem of starvation. There is a problem of deadlock. What is the problem? Let's give our first attempt. If I am a particular philosopher PI, what will I do? I will first think. Think means some computation. Just think about the process is doing some computation. Now suddenly it requires the resource. You take the fork I, the left fork. Take the fork I plus 1 mod n, the right fork. Eat, that is, you use the resource. Okay. Use the resource. Put the fork, put the left fork, put back the right fork. Good enough. This is what we decided the algorithm. But the problem is, this is not a fair solution. If two processes, because there are only 5 forks, you can at max give 2 processes 2 forks. What about the rest? They don't have a fork. So it's a starvation situation. It's not a fair situation. So what is the solution then? Anyone? How can we come out of this starvation? Can you give me a solution? No? Okay, let's look at the situation. We will impose a condition that if you are taking the fork, if you have taken the left fork, look at this. You have taken the left fork. Good. But for taking the right fork, you first have to see whether it is available or not. If it is not available, you put back the left fork. What am I doing? See, I need 2 things. If I have got the left one, I have not got the right one, I know that I cannot progress. So why are you unnecessarily holding the left fork, and you are creating trouble for the person who's sitting next? Because you are not getting the right fork, you cannot proceed. So better you keep that, drop it. Drop one, drop the left fork that you have picked up. That's what it says. Why? So that somebody else can get it. That's the idea. So if the philosopher has picked up the left fork and it sees that the right fork is not available, that is, the resource is not available, you put back the one that you are holding now so that somebody else can take it. Will it solve the situation? Will it solve the situation? What do you think? Will it solve the situation? No. Why? Because I may put down the left at the same time and this will go on. See, your 5 friends are sitting in a round table. Everybody decides that everyone picks up the left fork. But the problem is, when I see that my right fork is not there, I was told that please put down your left fork. Okay. But everybody puts down at the same time. And again, they pick up the left one and everybody sees that the right hand side fork is not there. This goes on. Everybody picks up the left one and the right is not there. So what is the problem? What is the solution to this? The solution is that when you put back the fork, do not put back all at the same time. Take a random time to put back. So they will wait for a random time and then you will put back the fork so that somebody gets both the forks at the same time. This is the condition. So there is less likelihood of deadlock. Why it is deadlock? Because everybody is having a left and my right is dependent on your left. When you will put back your left fork, I will get back the right fork. That's the deadlock situation. So if both of us are putting up and putting down at the same time, I will never get my right hand side. That is only possible if we have a different timing at which you put back and I take. Okay, this is the situation that solves the problem. Now you may say that, okay, fine, this is a good solution. You are okay, very happy. But once in 100 such things, there can be a possibility where, all of them, it's this random timing that you are saying is not absolutely random. There can be one such situation where again, there can be all of them putting back at the same time. Maybe that possibility is 1 in a million, but there is a possibility. So think about situations such as you are controlling a nuclear power plant. It's a very, very tricky situation. Even 1 in a 1 million chance cannot be allowed, because if that happens and if there's a deadlock, then your entire plant gets shut and there can be some catastrophic thing. That is not allowed. Okay, for soft problems like network packets are getting disturbed, network packets are colliding, you do take a random time. Suppose a packet you are sending, it's colliding. Okay, fine. You wait for some random time and then send it again. Possibly next time will be what maximum has happened. You have delayed that. But it's okay. That's not so big a problem. Problem is if you are handling such tricky situations such as nuclear power plant. What doing a mutex based solution? Mutex based solution is okay. But the problem is if you apply mutex, you are actually allowing only one process to proceed. Only one process to proceed. And that is a huge hit on the performance. Huge hit on the performance. Okay. So what is the idea behind the solution? The solution is you first decide on the state. And this is the solution that I'm proposing from your textbook. The solution is this. You use n semaphores. Look at this. You use n semaphores, all initialized to 0, and 3 states. They are called hungry, eating, and thinking. And the condition that we impose is a philosopher can only move from an eating state, move to an eating state, if neither the neighbor is eating. Let's have a look at that. Okay, here is the philosopher process. What does the philosopher do? Think, which is nothing but a computation. Take the fork, eat, and put the fork. Good enough. Take the fork, eat, and put the fork. What is this take forks? Take forks is the process where you are checking 2 things, the state, and then you are incrementing the mutex, or you are decrementing the semaphore. What is the semaphore doing here? The semaphore is keeping track of how many other philosophers want that particular. That's it. How many other philosophers want that particular form, the one that you are holding. So what we do is, the first thing we do is we make the state equal to hungry. That I am hungry, only then I will be eating. I will unlock this mutex and I will down the SI. Down SI means the semaphore on which the other processes are waiting. Okay, so SI is my semaphore. I immediately make that equal to 0 so that my semaphore is not disturbed. This is what we do in take fork. Then eat. What do we do in right put fork? Go back to the solution. We said you put back your fork if you see that your neighbor is eating. That means it's already engaged, so you put back the fork. So what we do is we change the state to thinking, number 1, and then we test. Test what? The left and the right. This is testing whether my left neighbor and the right neighbor, what is the state of theirs? Let's look at the test function. What do we do in test? We check the state of I. If it is hungry and the state of left is not eating and the state of right is not eating. Go back to this. A philosopher will only move to eating state if neither neighbor is eating. So I'm checking whether my left neighbor is eating or my right neighbor is eating. If neither of them are eating and I am hungry, then your state is eating. Okay, this is the idea. Fine. So this is about the state. What about this? Suppose you are eating, that means you are in the critical section. So you should up anyone who's waiting in that particular semaphore. This is the condition which ensures solution to the dining philosophy. Okay. This is the solution that I have taken from the textbook. There are a lot of other possible solutions and other variants of that as well. We will talk about that later on if time permits. So that's about it for today's lecture.